We are on 9.4 today, which is common logarithms. So common logarithms, we're going to talk about a little bit today, and these are probably it's in the word common, but these are probably the most useful in terms of solving logarithmic equations. Because before, when we had exponentials or things, we'd rewrite them in logarithmic form using a different base. Common logarithms are in base 10, so we can actually use our calculators to help us solve these. So just a few definitions and explanations here. We're going to look at common logarithms, or just logarithms in base 10. So we would anything log base 10 of 5, log base 10 of 100, doesn't matter what it is, it's always in log base 10. The subscript 10 is usually omitted when writing common logarithms. You don't have to write it. If you just say log of 5, that really means log base 10 of 5. The log key on most scientific calculators is used to evaluate common logarithms. So that log key that you've seen in your calculators, we haven't been able to use it yet because it's base 10 and we haven't been in base 10. So now that we're in base 10, we can actually use that logarithm, the calculator function, to help us solve these. So we're going to go ahead and take a look at a few examples here of how do we use the log base 10. How is it different or more useful to us? So the first thing we're going to do is just take our calculators, and I want you to practice using it by just typing in log 3. So it's not in a base or anything else, it's just log 3. So it's over there on the left-hand side on most scientific calculators. Hit 3 and hit enter, and you should get, now take these out to 4 decimal places. This is very typical for logarithms. 4 decimal places. So for this one, it was 0.4771, and make sure to properly round the last one. And then again, log of 0.2 gave me a negative number. So it was negative, which can happen, 0.69. Now it goes 897, so the 7 rounds the 9 up, so it ends up rounding it all up, so it's 90. So make sure you properly round all of those things. So that's not hard. So let's take a look now at how do we use this to solve some equations. How is this more useful than what we had been doing? So when we look at solving 3 to the x equals 11, if I were to rewrite this in logarithm form using our base, what we've been using, I would have log base 3 of 11 is equal to x. That's great. But I can't get 11 to be 3. I don't have any other numbers or information as to how to break up 11 and what log base 3 of 11 is. So I'm stuck. This stops. I don't have anywhere to go from there. So what we do now is almost just kind of like you multiply or divide both sides by something. I can take the log of both sides, the common log. So it's log of 3 to the x is equal to log of 11. So this didn't help us, so we don't want to do that. But by taking the log of both sides, this goes in my calculator. I can figure out what log of 11 is. Over here, we're going to use that exponent power property of logarithms to pull the x out front. So I now have x times log of 3 is equal to log of 11. Now this log of 3 is just a number. I can put it in my calculator. So I can divide both sides by log of 3. And then in my calculator, I'm going to put in log of 11 divided by log of 3. Now when you do that, make sure to close off your parentheses. You want to hit log of 11, close parentheses, divided by log 3. Close parentheses, hit enter, and you should get 2.1827 is the answer there. And don't do the logs until the very, very, very end, because you don't want to round off too many times and make your answer inaccurate. So let's go ahead and try another one of these, just so you guys can kind of get the feel and see how this is working. Again, 4 to the x is equal to 15. If I did what we used to do, we'd have log base 4 of 15 is equal to x. Again, variable separated with something over here. I can't get 15 into a 4 or anything else with the same base. That breaks into 5 and 3. I don't know what the log base 4 of 3 is. that doesn't work. So what I'm going to do is take the log of both sides. So I'm taking the log 4 to the x equal to log of 15. Again, the exponent comes out front. That's the property of logarithms that we discussed in section 3. So now I have the log of 4 is equal to the log of 15. I can divide by the log of 4 because it's just a number. And then my final answer ends up being whatever log of 15 divided by log of 4 is. And we get 1.9534. 1.9534. So that's the first part of this. That's probably one of the more useful ways that we can use logarithms, is by doing simple problems kind of like this, by taking the log of both sides. So we're going to look at a few more examples, getting a little more complex in nature. Some inequalities. So now we're going to look at how do I do and solve an inequality that we need to use the common logarithm for. Okay, so again we have 5 to the 3y less than 8 to the y minus 1. When I do this, excuse me. So again, I want to get those variables out of there. I want to try to get to those variables in the exponents, but I can't do that because 5 and 8 cannot become the same base. There's no way to rewrite those to get the same base. So I'm going to go ahead and take the log of both sides. So we have log 5 to the 3y is less than log 8 to the y minus 1. Again, exponents out front. So we have 3y log of 5 is less than the quantity y minus 1 times the log of 8. So now I'm going to divide both sides by the log of 5. So we end up with 3y is less than y minus 1 times the log of 8 divided by the log of 5. Again, it's going to get kind of messy with the two logs in there, but don't divide those out until the very, very end so you're not rounding too many times. And now I'm going to divide by that y minus 1 because it's a whole quantity, and that will allow us... actually, you know what? I just made a mistake. You do want to divide that out so that we can distribute it. I'm sorry. I think you have a different problem set. So you do want to divide this out so that we can multiply through and get an actual value so that we can solve for y. So typically we don't, but for this particular problem we do. So log of 8 divided by log of 5, and that's going to give us 1.2920. So we have y minus 1 times 1.2920. And if I distribute that, I'll be able to solve for y. So we'll have 3y is less than 1.292y minus 1.292. Okay, I just distributed that to both things there. Then I subtract this. So we get 3 minus 1.292. We get 1.708. So we have 1.708y. Then we just divide by 1.708. So like I said, these are a little more complex in nature when you have variables on both sides. So that does change things up a little bit here. So we end up with a negative 0.7564. Negative 0.7564. And again, we're allowed to get a negative number there because the initial problem didn't involve logarithms, so I could have a negative number. That's okay. Alright, take a minute or two and try and solve the second one on your own, and I'll come back here in a second and give you the full solution to it. But try to go ahead and start and try to do that one on your own using the common log. So we're going to take the log of both sides, exponents out front, so we have 2x log of 3 is greater than the quantity x plus 1 times the log of 6. Divide by one of the logarithms, so we have 2x is greater than quantity x plus 1 all over log of 6 divided by log of 3. Again, I'm going to go ahead and do that this time so I can distribute through, so I can actually get an answer there. So we're going to have the log of 6 divided by the log of 3, which is 1.631. Distribute that. Subtract it. So we end up with 0.369 x is greater than negative 1.631. So I divide and end up with x being greater than negative 4.42. And that would be your final answer there. And again, because there were logs initially involved, we don't have to worry about x or negative things there. Alright, so now we're going to look at how we can actually change the base of things. So if for some reason you wanted to put something in the common logarithm, so it's not given to you in base 10, but you want to use it in base 10 so that you can use your calculator to solve it, you can go ahead and do that using our base of change formula. I'm sure you're hearing formula and like, oh no, this is going to be tough. It's actually not. It's just taking two different things and dividing it out. So initially, look at this. We have the log base a of n is equal to whatever base you want it to be is what you're going to make the base. And I take the original bigger number, the one that we're taking the log of, divided by the log of the base. So for instance, if I had one of those things we had before, so I had like log base 4 of 6. So I can't get 6 to be with the base of 4 or vice versa or whatever. I could take and rewrite this as the log of 6, remember that's base 10, divided by the log of 4. And now my calculator will actually tell me what that base or what that logarithm is using the change of base formula. You're just doing logarithm division. So log of 6 divided by the log of 4 ends up giving me 1.2924, or 25, excuse me. 1.2925. And that's the value of log base 4 of 6 using the change of base formula. So they say take log base 4 of 25 and express it in terms of the common logarithm and then estimate it using the calculator. So when I do this one, again, we're just using the change of base formula. I have log base 4 of 25. I cannot rewrite either of those in the base of the other one. So I have to use log base 10, or just log of 25, divided by the original base. So now I've changed them both to base 10. I can divide them out, and we can get an approximation of what that's going to look like. It's going to be log of 25 divided by log of 4, and we end up with 2.3219. Alright, so let's look at this word problem and how we can use logs to solve it. Because there are some practical applications to logarithms and how we can use them to help us solve some problems. So it's the amount of energy in ergs that an earthquake releases is related to its Richter scale magnitude, m, by the equation log of E is equal to 11.8 plus 1.5 m, where m is that magnitude. The Chilean earthquake of 1960 measured 8.5 on the Richter scale. How much energy was released? So we have our equation, log of E is equal to 11.8 plus 1.5 m. Now they tell us that it was measured at 8.5 on the Richter scale. That means this m is going to be 8.5. So we have log of E is equal to 11.8 plus 1.5 times 8.5. So let's simplify a little bit. So we have 1.5 times 8.5. We get 12.75. And we want to add that to 11.8. 24.55. So now that I have log of E is equal to 24.55, how do I change that? How do I use that? Well, remember this is base 10, so I can write it back in exponential form. So you might want to do that sometimes. We have 10 to the 24.55 power is equal to the amount of energy that is. So if I were to figure that out, and just, if we were to do that very quickly, it's going to end up being this number. So the amount of energy released was 3.5481 times 10 to the 24th power. So 10 to the 24, that means we're moving it 24 places. So just to kind of give you an estimate of what that would look like. It is 3 and all of those numbers and zeros. So that's how much energy is released on that high of a magnitude of 8.5. Now again, 8.5 is a very high magnitude earthquake. But that is a lot of energy because these are hundred thousands, millions, billions, trillions, quadrillions, quintillions, septillions. It's all the way beyond what we usually count. Alright, so your homework for this section is 531, 15 through 35, or 33 odds, excuse me. And that'll be the assignment we work on in class.
You, pretty chitty bang bang, chitty chitty bang bang, we love you. And in chitty chitty bang bang, chitty chitty bang bang, what we'll do near, far, in our motor car, oh what a happy time we'll spend. Bang bang, chitty chitty bang bang, our fine four-fender friends. Bang bang, chitty chitty bang bang, our fine four-fender